point of view. As it was said, the topic of the talk today is delamination, propagation, and load ratio effect in a DCB multi-directional moving composite specimen. So the presentation layout will be as follows. First, a quick introduction will be explaining the motivation and the material investigated. Then the results of constant amplitude fatigue tests conducted under different R ratios will be presented. Following that, the Hartmann-Skyver master curve representation and its modification will be shortly discussed. Also presenting the master curve and the DADN curves back calculated for me. Finally, conclusion will be given. So let's say we have an aircraft, and it can be one of the new commercial airplanes like the Boeing 787 or the Airbus 350, in which composite materials take up to 50% of their weight. One may map the loads this aircraft may experience during its lifetime, and from a damage tolerance point of view, we want to know how the delamination already present in the aircraft will grow under this kind of load spectrum. The load spectrum may be presented as built-up of blocks, which may be described by the maximum and minimum loads in the fatigue cycle. And another parameter which may be introduced, which was already talked about, is the load ratio, which is simply the ratio between the minimum and maximum loads. As you may notice here, there is an enormous number of load ratios in this spectrum, and we want to know how the delamination will grow under this. If you want to know how the delamination will grow under this spectrum, we will need to know how each one of the load ratio will affect its growth. This may require a large number of tests. So we want to only conduct a small number of tests using a small number of load ratios, and from those tests to be able to predict how the delamination will grow in every load ratio. The material investigated here is a composite laminate composed of 15 plies of G10814 pre-preg plain woven carbon fibers in a 913 epoxy resin. The layup is a multi-directional one in which each ply was rotated 45 degrees in respect to its previous, and a 25.4 micrometer thick PTFE insert was placed between the 7 and 8 plies, acting as an initial delamination. The tests were conducted on double cantilever beam specimens under displacement control, replacing the load ratio with its displacement equivalent to the displacement ratio, which is the same thing, the ratio between the minimum and maximum displacement in the fatigue cycle. So 8 constant amplitude fatigue tests were conducted using 4 displacement ratios, 0.1, 0.33, 0.5, and 0.75. This is a quick summary of the test results, or the test, and you may notice that 2 specimens were conducted for each displacement ratio, and that there was a slight mismatch between the pre-described displacement ratio and the resulted load ratio. The test duration was between 1 million to 3 million cycles, and everything was conducted in the environment. So the delamination propagation rate was plotted firstly versus the normalized maximum energy release rate in a fatigue cycle, which is simply the maximum energy release rate divided by the delamination resistance or delamination toughness. It was calculated from quasi-static tests which were conducted earlier, and I'm not showing you it. A schematic presentation of the load ratio effect when G1 max is used may easily be found in the literature, and it simply states that the ADN curves are, the slopes of the ADN curves depend heavily on the R ratio, but they all share a common critical value for which the delamination will propagate catastrophically, and each one of them has a different threshold value for which no propagation will propagate. And the second parameter which was used is the normalized effective energy release rate range, which is simply the square root of G max minus the square root of G1 min to the power of 2. And currently there is no consensus in the literature on the effect of the load ratio on the full DADN curve when delta G1 effective is used, and it was also talked somewhat about in the previous lecture. Those are the test results plotted in respect to G1 max hat. As you can see, the behavior is as expected from the schematic presentation, and all the curves rise to a common threshold value. It's the normalized critical value, this is why it's 1, and that the slopes are dependent on the load ratio, on the displacement ratio, and differ between 6.8 to 25.5, and you can see that the smallest slope related to the smallest displacement ratio and the highest to the highest. Those are the test results where it's plotted in respect to delta G1 effective had. The same dependent on the displacement ratio is seen here, meaning that the lowest displacement ratio has the lowest slope. And you can also see there's a slight mismatch between the slopes shown here and the slopes shown when Gmax is used. So, as I told you before, when plotting in respect to G1 max, the schematic representation I showed you before, we can see it behaves the same. But when plotting in respect to delta G1 effective, it's when looking at it, I can assume that it's the behavior is different from this one, or you can see it's different, but that the schematic representation looks something like this, and then that all of the ADN curves share a common threshold value. And if this is true, then those two parameters, G1R and delta G effective threshold, are laminate constants that are unaffected by the R ratio, and can maybe use to use in formulation of the master curve. So Jones et al. Presented a function of the energy release rate, which was talked about, that is based on the work of Hartman and Skyma. And when this representation is used, all the empirical data collapse into one curve. Here, a different parameter was used. It's delta square root of G1, which is simply the square root of G1 max minus the square root of G1 mean. And the parameter delta square root of G1 threshold is a threshold of this parameter. In the paper, they stated that those two parameters are chosen so the equation best represents the experimental data. Since G1 mean is considered less accurate than G1 max, the Hartman-Skyma representation may be modified to be a function of only G1 max, and this was used in the previous talk. And here you should remember that the G1 threshold is a function of the load ratio, as we are seeing here. So we can fix it by using the relation between delta G1 effective and G1 max, and assuming that when G1 max goes to its threshold value, also delta G effective goes to its threshold value. So now we have an expression that relates delta square root of G1 threshold to delta G1 effective threshold, and I remind you that our assumption that this is a constant for all load ratios. And finally, the energy release rate may be normalized using the G1R value, eliminating the need to determine a value for GC, and thus the modified Hartman-Skyma is given by this formulation, which was named here delta K bar. And now, only one fitting parameter must be chosen, which is delta G1 effective threshold. And if we assume that the behavior I showed you before is actually happening, then I can plot that of delta G1 effective in respect to the cycle number on a log-log scale, draw straight lines through the data, and this point, the interception point, is actually delta G1 effective threshold. As you may see here, there's no clear interception point, but it's somewhere in the range between 0.3 and 0.04. So I can take this and plot the master curve, which is the ADN versus delta K bar. And you may notice here that the value used is 0.0365, which is in the range I talked about before. And it gives a pretty good results of the master curve. And that the slope of the master curve is 5.8, which is lower than the other ADN curves, but it's a bit still high if you are going to something about around 2 or anything like that. I can use this master curve to back calculate the ADN curves for the other function. Here it was done for delta G1 effective, and you see it fits pretty well with the test data. And here that was done for G1 max. And that's it now for conclusions. So 8 mode 1 constant amplitude fatigue tests were conducted using 4 different displacement ratios. A clear dependence of the delamination propagation rate was seen when using the ADN and when using Gmax or delta G1 effective. But when the empirical data is plotted as a function of delta K bar, all of the empirical data collapse into one master curve independent of the displacement or log ratio. Only 2 laminate constants are needed in order to calculate delta K bar. G1R, which may be found from quasi-static tests, and delta G1 effective threshold, which I showed you how is way to estimate it. Now, using the calculated equation for the master curve and the log ratio values, the fatigue curves may be back calculated for any log ratio, regardless of the function used for plotting. And this is what we were set up to do. And also, it's suggested here that the threshold value may be used for no gross design purposes, regardless of the anticipated log ratio. But it should be noted that this value is based on the suggested master curve model and is lacking an empirical confirmation. Thank you.